Hi everyone, welcome to the last day of our event. It's a great pleasure to receive you here and also to host this event. It's a great pleasure. And to start, we have two messages from both of our main sponsors. First, from ISPRS Student Consortium President Cheryl Rose Reyes.
Hi everyone, my name is Cheryl Rose Reyes, and I currently serve as the president of the International Society for Photogrammetry and Remote Sensing Student Consortium. I am very happy to welcome you all to the 6th edition of the IEEE GRSS Young Professionals and ISPRS Student Consortium Summer School this year. To start this event, I would like to present a bit about the ISPRS Student Consortium. We are the official representation of the youth to ISPRS. We link students, young researchers, and professionals worldwide interested in photogrammetry, remote sensing, and spatial information science to promote their scientific and professional developments. We advocate imaging and geospatial science for informed, scientifically valid, and technologically sound observations of Earth conditions and trends that lead to improved and effective decision-making. The consortium is also accepting registrations for individual membership. Please scan the QR code in this slide if you are interested to join us. I work together with members of the board of directors from all across the globe. Charles from Uganda is our vice president. Charmaine, who is currently in Ireland, is in charge of our newsletter. Mustafa, our social media administrator, is from Turkey. And finally, Sona from Azerbaijan is our web administrator. One of the major events that we host and coordinate every year are the summer schools. In 2019, the summer schools were in Uganda, Poland, South Korea, and Brazil. These summer schools provide international learning opportunities for students and young professionals at a minimum cost. This year, we scheduled 3 summer schools, but due to the COVID-19 situation, 2 of them were postponed, and we are sincerely thankful to the organizers of this summer school for making this an incredible virtual event. This is the first ISPRS Student Consortium Summer School that will be hosted online, and as you can see, we have an amazing lineup of speakers who will deliver lectures on remote sensing and machine learning. The consortium currently hosts the virtual rooms and the webinar series to provide our community with more opportunities to learn and interact with experts in our scientific community. The webinar series was conceptualized in 2018, and we have organized webinars on Google Earth Engine, computer vision, and machine learning. The virtual rooms is an initiative to keep the members of the consortium connected during this challenging time and to help them navigate our changing lifestyles. All the resources for the webinar series and the virtual rooms are available on our website and our YouTube channel. We also publish an official newsletter called SPECTRUM, which covers the broad applications of remote sensing, photogrammetry, and spatial information science, and welcomes contributors from diverse backgrounds and disciplines. We publish 4 issues a year, and our most recent issue is related to the current pandemic and the significance of geospatial information in tackling the impacts of this global health crisis to our society. The ISPRS Congress is one of the biggest gatherings in our scientific community, which is held every 4 years. The Congress hosted a virtual event for all papers submitted this year and postponed the in-person meeting for 2021. During the Congress, the consortium will be hosting a 3-day youth forum, which will feature the following activities: speed dating, technical sessions, a special session on women in remote sensing, photogrammetry, and spatial information science, a panel discussion, the General Assembly for our members, a student night, another summer school, and will co-organize a mapping party. The consortium would also like to invite you to nominate papers for the Excellence Award to be given during this event. Please scan the QR code for eligibility and nominations. Also, please visit the ISPRS Congress official website for updates. Finally, I would like to invite you all to join our communities on Facebook, Twitter, and to visit our website for all the information shared in this presentation. And again, I would like to invite you all to register as an individual member by scanning the QR code on the right. This is the end of my presentation, and I wish you all a meaningful summer school. Thank you very much.
Thank you, Cheryl, for your message. This is a recorded message from Cheryl that we had the pleasure to have her here with us. Thank you, Cheryl. Thank you a lot. And now I would like to ask uh, to present the GRSS video from Paulo Gamba.
Good morning, my name is Paulo Gamba and I am the president for the year 2020 of the Geoscience Remote Sensing Society. Okay, so first of all, what is a scientific society? What is GRSS? So a scientific society is a group of scientists, researchers and practitioners with common interest and common framework for building a community. In our specific case, we are people who are dealing with theory, concept and techniques of science and engineering as they apply to remote sensing of the Earth, ocean, atmosphere and space, as well as the processing, interpretation and dissemination of this information. So what are the activities of the IEEE Geoscience and Remote Sensing Society? Well, we have a number of applications. We support conferences. We have professional activities. We have a number of information service and technical activities and education activities as well. We are a global community, which means that we are arranged around a large number of groups of people that we call chapters all around the world. We have currently more than 90 chapters all around the world. As a result, GRSS disseminates premium science by means of its three main journals, which are the Transactional Geoscience Remote Sensing, the Geoscience Remote Sensing Letters, the IEEE Journal of Selected Topics in Applied Earth Observation and Remote Sensing, but we have also a magazine, which, by the way, has a very, very important role. We also provide opportunities for the different communities, like, for instance, the community working on image analysis and data fusion. We also sponsor community-driven events, like the very successful Earth Vision workshop, but also the SpaceNet Challenge data challenges here, which is organized by SpaceNet. We support also community-developed tools like the DESE website, which is Data and Algorithm Standard Evaluation website, and also activities related to RFI observations. So we also facilitate and connect. We have a number of activities at in our main conference. We have the so-called TIE events, but we also organize different events related to connection with companies, industries. We have a number of activities like for young professionals, for women in engineering and in geoscience and remote sensing. And we share our knowledge on hot topics by means of distinguished lecturers and industry speakers. We have also a number of educational activities. This is one of them. This is basically, let's say, one of the many different small educational videos for kids that we have in different languages, but we have also, in addition to that, a number of webinars, which are also for people who are not kids, about remote sensing in different languages as well. We offer continuing education by means of webinars, which is especially important and useful in this situation where we are not able anymore to move around the world as we were in the past. So we can support continuing education of students and young professionals through conferences, journals, our magazine, webinars, and so on. We can promote capabilities of the different communities, algorithms, data set by means of the data fusion context, by means of dedicated events at our conferences, by means of the industrial distinguished lecture or industrial speakers. We help connect companies and young motivated people by means of the Young Professional event, by means of student grants, by means of the TIE Forum. And we make the different community of Earth observation practitioner and researcher be aware of their and your topics of interest. So GRSS is actually a community of communities where we could together share and promote ideas, systems, and data set. We can meet with other communities and gain from their perspective, and we can build different collaboration to learn more from each other's and to come together in conferences. Thank you very much, and I hope you will enjoy this summer school and all the interesting topic and talks that you are going to listen during these days.
Thank you, Paolo, for your message and also from your support. Now it's time to start our lecture today. I would like to invite to the room Professor Antonio Tomaselli from São Paulo State University. Thank you, Professor Tomaselli, for accepting our invitation. It's a great pleasure to have you here. And now the room is yours. Thank you again.
Thank you, Marcato. Thank you, your officers from GRSS for this invitation. Good afternoon, good evening, and good morning, depending from where you are, and welcome all attendants. This is a section of the IEEE GRSS Young Professionals and ISPRS Student Consortium Summer School. These meetings are usually organized in Brazil and supported by both IEEE Geoscience Remote Sensing Society and ISPRS. I am Antonio Tomaselli from Unesp, São Paulo, Brazil, and I am the chair of this section, together with Marcos Chimalski from UDESC, University of the State of Santa Catarina, Brazil, and Sherry Rose Reis, president of ISPRS Student Consortium. This presentation will focus on hyperspectral imaging in agriculture and forestry applications, and will be delivered by Eija Honkavaara from the Finnish Geospatial Research Institute in Finland. Dr. Eija Honkavaara is research professor at the Finnish Geospatial Research Institute in the National Land Survey of Finland, and also docent at the Aalto University. Today, her research focuses on drone-based remote sensing, photogrammetry, and hyperspectral imaging, and their utilization in intelligence-based environmental applications, especially in forestry and agriculture. She's leading the working group Hyperspectral Image Processing in the International Society for Photogrammetry and Remote Sensing. So, Eija, please, floor is yours for your presentation. Thank you very much again.
So thank you for inviting me to this event, and good morning, afternoon, and evening to everyone. I hope you can hear me now. Please let me know if you can't hear or see my presentation or me. So thank you, many thanks to Professor Tomaselli for introducing me. So, as he told, I'm Eija Honkavaara, and topic is hyperspectral imaging in agriculture and forestry applications. And first of all, I would like to thank all my colleagues from our institute who have been working with me with these topics. So this is group work, what we have been working, and I'm presenting some of our results. Content of presentation is the following. I have 3 parts here. So first of all, I will discuss about hyperspectral sensors. My presentation will focus drone-based hyperspectral imaging. Then I will talk about quantitative processing of data, and then I will have some examples from use cases of hyperspectral drone imaging. So about the background and objectives. Multi and hyperspectral sensors, they are used to capture spectral information of objects in order to make detection, classification, analysis, and so on. And the difference between hyperspectral and multispectral imaging is that hyperspectral sensors, they aim at reconstructing the continuous spectral signatures of objects, and because of that, they are using tens to hundreds of narrow spectral bands to do this, whereas multispectral cameras, they typically use something like 3 to 10 selected spectral bands that have been optimized to some specific spectral areas of interest. And during a few past years, development of these miniaturized spectral sensors, it has been very fast. So tens of different alternatives have come available, and they are affordable and high quality. Use of multispectral sensors is very, very extensive, but hyperspectral sensors are not maybe used so much yet in practice. They are mostly used in science and research. So in comparison to multispectral sensors, they are still relatively expensive. So it's not possible to, in all cases, to establish low-cost applications. They can be also heavy, and they are often more challenging to operate and process. There is also some questions that how this more precise spectral data can be utilized in practical applications. What are the advantages of this better quality? These are questions what we are also trying to solve in our research here at FGI, and also many other researchers around the world are working with these topics. So at FGI, our important research objectives are to develop and utilize new drone-based hyperspectral imaging technologies in remote sensing. Especially, we are concerned about quantitative processing and analysis of the data. We are also, when we are developing our processing chains, we are concerning about data fusion to integrate all important data sets to the analysis process. We also make comparisons of hyperspectral and multispectral and try to find that what are the advantages of different sensor technologies. And in our development work, some of our topics of interest are to develop methods for autonomous operation and real-time operation. So as there are more and more drones and they are collecting more and more data, it's more difficult to download these data sets to some computer after a flight and then start processing. It takes too much time. So real-time and autonomous and efficient processing chains are very interesting. And at our institute, major applications for hyperspectral imaging are precision agriculture, precision forestry, and environmental remote sensing. So when we are talking about agriculture and forestry, of course, our important topic is vegetation. And this is what I'm illustrating in this slide. So by hyperspectral imaging, we are trying to characterize the spectral signature of vegetation and trying to make analysis of vegetation using this data. Typically, we divide these areas of interest to visible from 400 to 700 nanometers, near infrared from about 700 to 1,200 nanometers, and shortwave infrared from about 1,300 to 2,500 nanometers. You can see these ranges here. And then, of course, the question is that what can we see then in these different spectral ranges? So in visible range, we typically are analyzing leaf pigments, especially chlorophyll A and B. This chlorophyll is linked to health and quality of the plant, and it's indicating photosynthetically active radiation observed by the leaf, and it can be used as an indicator of plant productivity. And the major areas here are these blue and red absorption areas. And in near infrared range, the reflectance, it occurs at the cell walls, and there we are analyzing this red edge. The slope of red edge, it indicates plant stress and also gives indication about chlorophyll concentration. And then this near plateau, it tells about changes and differences in cellular levels, including hydration and health and biomass of the plant. So with this analysis, we can get information, a lot of information about the plants. Then there is this shortwave infrared region, which is still less used, but it's coming available also in commercial systems. So there, the major concern are the water absorption bands, which are found in several positions in the sphere range, and they can be used to analyze plant water content, which tells about water deficiencies, some illnesses, maybe about some pests, and also it can be used to predict forest fire risk. And here is another presentation about this same topic. So here is this visible to near infrared red range, which is the most commonly still used in commercial applications. And here we can see examples. This green shows healthy plant, orange line shows stressed plant, and then brown line shows soil. So the hyperspectral sensor, it's trying to reconstruct the whole spectrum of the object, whereas here we have a 4-band multispectral imager, which is concentrated in this green reflectance region, and then in red absorption region, and then red edge and near infrared areas. So this is optimized, this spectral response of this multispectral sensor then to characterize plant health. And here are examples of sensors what we can use to make this kind of analysis. Here is this very popular MiCalSense Altum multispectral camera that records 5 bands. And here we have again plant that is like dying or in bad health and good health plant. And then our hyperspectral camera then reconstructs the spectrum here at much higher resolution. Okay. So about hyperspectral sensors. So there are many different kinds of sensors available in the market. They are typically divided or classified as point spectrometers. So point spectrometer is recording one point at a time. Then PUSHBROOM scanner, it is recording and scanning the object line by line. So this vertical axis shows the spectral resolution, and then this horizontal axis, they show spatial resolution. Then we have 2-dimensional hyperspectral cameras, and there are very many different types of sensors. There is this article by Helge Aasen, and what I'm here referring, it tells a lot about different sensors. here is just a list showing that there are really many different alternatives. And how this spectral measurement is made, it has great impact on spectral, radiometric, and spatial characteristics of data. It has impacts on quality of the data and also how the data can be processed. So when buying sensors, it's important to consider these aspects, that how well different sensors are serving. Then one quite significant difference between these different sensor types is also that what kind of spectral resolution one can obtain. So typically it goes so that with these point spectrometers, we can get very high spectral resolutions, well below 1 nanometer. So it's can really get this continuous characterization of the object. Then PUSHBROOM sensors are typically approximately, many of them are on the level of 2 to 5 nanometers. And then when we are talking about two-dimensional cameras, they are typically at least above 5 nanometers, this full width of half maximum and even more. So this is one difference between different sensors also. And as we are talking about imaging sensors, I'm showing these two types of imaging sensors. So point spectrometers, typically they don't really give you good quality images. So when we are talking about imaging hyperspectral sensors, we are using PUSHBROOM sensors or these two-dimensional cameras. So about PUSHBROOM sensors, PUSHBROOM scanning is the most used hyperspectral imaging technology. And with the good quality sensors, it's possible to get very high spectral quality data. And also manufacturers, they are offering and providing accurate calibrations for the sensors. This kind of high-end systems, they are still quite heavy. They typically weigh about 2 to 6 kilos. And from these PUSHBROOM scanners, it's possible to get very wide, or this full reflective range can be covered with these PUSHBROOM sensors. They are commercially available, these sensors already. And they can be divided to visible near-infrared, extended infrared, near-infrared, sphere, or then full reflective range. So everything is available on the basis that what you need and how much you don't have money, because these full range cameras are of course the most expensive ones. Challenge with these PUSHBROOM scanners is that it's highly dynamic, this imaging principle. So you need very accurate GNSS IMU to be able to georeference and rectify and georectify the data. And then, but also some image-based structure from motion-based solutions can support this reconstruction. There are some specific processing systems then for these. Of course, there are systems by researchers, but for companies, there are some like this RESE, ATCOR, and PARCH. They are very popular processing systems for hyperspectral PUSHBROOM imagers. Then about this two-dimensional imaging principle. So this is relatively new technology. It has been available maybe starting from 2010. As I mentioned, there are many different alternatives. For instance, there are these snapshot imagers that record every band at the same time. And then there are different tunable filters. I will give an example about this tunable filter system. Advantages of these sensors are that they are providing stereoscopic data. Georeferencing is more simple than with a PUSHBROOM, and we can have hyperspectral 3D data. We have multispectral data, And in principle, this data can be processed using mainstream photogrammetric and machine vision methods, which makes it much easier to implement in the systems. There are some challenges also, like with the tunable filters. You will see that there are some alignment problems of the bands or challenges. And with mosaic filters and multi-point spectrometers, they have reduced spatial resolution. And in principle, these systems, they don't have as high quality spectral information as the PUSHBROOM systems. Here is one example of a hyperspectral imager. This is the FABRY-PEROT interferometer-based tunable visible near-infrared spectral camera by SENOP. And principle in this sensor is that there is a FABRY-PEROT interferometer in the optical path, and there is an air gap that is changed, and with different air gap values, we get a different spectral response. And when this is moved during the capture of single data cube, then we get different bands. And this is a little bit old model already from this SENOP camera. There are also newer ones. Newer one is faster, it gives more bands, and it has also integrated computer. So, and it can store more images and so on. But the principle is still the same. They are weighing less than 1 kilo, and it has a image size of about 1000 by 1000 pixels. And there are freely selectable bands, for instance, 100 bands or even more. And ground sample distance from 100-meter flying height is about 6 centimeters. With the same techniques, it's possible to make different spectral ranges also, like shortwave infrared or ultraviolet. But at the moment, the commercial systems from this version are invisible and near infrared range. And you can find more details from this internet page. They are the latest developments for the sensor. Here is an example then how this kind of sensor collects data. So parameters what we need in data collection is that we have to select the air gap values so that we have the desired spectral bands. User can select these as he wants. Then we of course give exposure time and interval for cubes. It can be, for instance, 3 seconds or 10 meters. And then we capture images because it's all the time changing this air gap. The bands are not aligned. So here are 3 band sets, and then the full data cube looks like this. So there can be a few meters difference between the first and the last image. It's of course dependent on how fast this scanning is made, and it's getting all the time faster. So this challenge is getting smaller. However, of course, when this kind of images are collected, so the basic data looks like this. So the bands are not overlapping well, and it has to be corrected somehow. And we have been developing different methods. There is the post-processing based method, and then also Professor Tomaselli's group has been developing this kind of a modified bundle block adjustment, how to have the bands together. So post-processing based approach is good for post-processing, but this kind of modified bundle adjustment is also suitable for real time. So in principle, the images look like this, but with these tools we can of course then match bands together, and then we have perfect data cubes. Here is a short view about how this miniaturized UAV spectral imaging has developed since 2008. So at that time, the cameras were mostly RGB cameras or modified RGB cameras. Then about 2010, there came available miniaturized multispectral cameras. In 2012, there were the first miniaturized hyperspectral PUSHBROOM sensors. Sorry. And then also this miniaturized sequential and hyperspectral 2D imager, the one what I just showed. Then after 2014, there has happened a lot. So at that time, there came many research groups were presenting their own solutions, self-assembled PUSHBROOM systems, also first PUSHBROOM systems for multi-rotor UAVs, also point spectrometers on board UAVs, also with wireless communication between ground spectrometer and the drone to make corrections to the data. And then there was this light field-based hyperspectral snap imager also coming at that time. Then afterwards, there have been sphere range 2D imagers and also these sun-induced fluorescence sensor systems since 2016. And maybe after that, it's difficult to tell what is happening because they are happening so much. Here is still one picture about hyperspectral cameras. So here in the vertical axis, there is a weight of the cameras ranging from some 100 grams to 6 kilograms. And then horizontal axis, we are showing different spectral ranges, what are available. So we see that there are a lot of sensors available, and these are just examples. There are much more you can find from internet, much more. And then we have to be a little bit careful because different manufacturers, they give a little bit different information. So in some systems can be really full systems, and then in some cases there can be like lens is missing or some wires are missing or so. So these are not totally comparable, but I think that this gives quite good picture that what kind of sensors are. So here in the left side, we have these 2D format sensors. So they are typically less than 1 kilogram, what I have found from internet. And the rest of all of these, they are PUSHBROOM type sensors, and there are really many different sensors available. As I mentioned, they are available from all possible spectral ranges in this reflective range. And there are some, for instance, we can see this here is head wall nano HYPER-SPEC, which weighs 1 kilogram. So it's one of the lightest PUSHBROOM type sensors. Then head wall micro HYPER-SPEC, it's 4 kilos. So it's probably a little bit older version technique, and also maybe higher quality or so. But yes, there are a lot of systems, and here also this full range hyperspectral imager. These are, I think, maybe quite new. So they are available, this kind of co-aligned sensors, which are integrating both visible near infrared sensor and then sphere sensor. So this is one way to do it. And then there's a specific this Corning micro HSE. It is actually single sensor solution. It has that kind of sensor solution that it doesn't have to co-align two different sensors. Then we go to the processing part. So I have named it quantitative processing because we see that it's very important when we are trying to measure with cameras, we need to have a quantitative processing, which means that we manage the uncertainties in this data processing chain so that we know that what is the quality of our analysis. And it, of course, involves both geometric georeferencing part and then radiometric part. I will focus in my presentation in this radiometric part. So first I'm showing here some sensor systems. I show here the systems from FGI, what kind of sensors we have been working with and developing these quantitative processing chains. So we have been working a lot with this SENOP tunable filter hyperspectral camera, and we integrate it with an irradiance spectrometer, which is used to measure lighting conditions. And then we have also integrated Applanix APX15, so it gives us RTK precision georeferencing. And then we also want to have 3D integrated, so we have dual RGB camera system to measure 3D structure of the object. And this is all integrated into one system, and it weighs a little bit more than 2 kilos than the whole integrated system. Then our second system, this is new, and we have just made our first experiments. So we have this FX10 PUSHBROOM scanner is still coming, and then we have this FX17 sphere range imager. So these are now our new systems. These are actually totally new in market also. They came this spring, and they represent quite modern technology. They have inside the system, they have computers, and they have precise Applanix APX15 GNSS IMU, and also storage unit in this same package. And they have 2,224 bands, and this is about FX10 visible near infrared. It has about 1,000 spatial pixels, and it has ground sample distance of 7 centimeters from 100 meter height, and then weight is 2.1 kilograms. And then this sphere range PUSHBROOM scanner, it has quite similar specifications, and it's only a little bit, it weighs a little bit more, 2.4 kilos. So this is something what is going to be used next summer more. Then we need a processing chain when we are talking about quantitative processing, and here you can see the principle what we are using. So we have data capture, we do some pre-processing, we do georeferencing, and then we do point cloud generation. So of course we don't do this point cloud generation in every system, like typically with our integrated RGB hyperspectral camera, we make point clouds from our RGB camera, and then we use this hyperspectral camera to give us the spectral data. And this process is made for forestry. So because we have very high resolution data, we typically do individual tree detection. Then in radiometric processing, I will tell a little bit more about this. This is important part in this spectral remote sensing. We calculate mosaics, and then we integrate our individual tree data with mosaics, and then we can have spectral information, and then we integrate it with reference data, and then we start make our estimation. I have a little bit different view about the same thing. Actually, here is one topic what we are studying also is this like machine learning and modeling. So this is a picture about that. Of course, we have exactly the same steps. This is now from agricultural application, but here is our machine learning based process. So here our objective is to develop model for analysis of the object. And then result is estimation model. And then another step in this kind of analytics process is this estimation and analytics. So we have, like in the previous figure, we had machine learning in the end, and output was estimation model. So now in the process, we principally have our estimation model also, and then our output is then here is like dry matter yield value map. This can be one output. So one question in this processes is that can we use our system to develop some estimation models and use these models more generally? And this kind of thoughts and systems have been developed based on this idea. But yes, I promised that I will talk about radiometric processing. So here I will show what this means. So when we are collecting data, typically the raw data doesn't look very nice. In cloudy conditions, when weather is changing, we get very varying radiometry for the image mosaics. Also, when we are collecting data at good weather, there can be many effects, and all these effects, atmosphere, illumination, object, and sensor and system, they are impacting our mosaic quality. So here is the first figure. What are the challenges in this radiometric processing? When we are recording the sunlight, we have the bidirectional reflectance distribution function, which means that when sun comes from one direction and we view object from another direction, always the reflectance what we see, it is dependent on geometry, on these relative angles of these, and it's visualized by this BRDF cake. So in the center is something what we see from top of the object, but then when we move and look object from different directions, then we have these different values. And then as I already showed, then second challenge is these different illumination conditions what we have to somehow take care in our processing. And this is the quantitative correction chain for reflective range. So we start by digital number of the camera, and then we have to do different corrections. First of all, we need to make some system artifact and radiance calibration. This is based on laboratory calibration. Then we have to take account some path radiance and adjacent effect, which are impacted by atmospheric constitution, different scatterings, and so on. And then we need to take into account the solar irradiance status. And these two are typical, they can be obtained in different ways. One way is to use some atmospheric modeling with radiative transfer codes like Modran, and many software are also implementing this kind of tools. Then we can use onboard irradiance data, and then also we can utilize image data to try to estimate that what kind of impacts these are causing. And then also we have to make BRDF modeling to be able to remove these BRDF effects. And finally, there are some shadow detection and correction. So these are also can be relevant to take into account. So if we are doing this full system, we are close to physical correction approach. But very typical correction is this empirical line-based transformation. I think that it's the most used in current system. So it simply is that we have some panels on object, and then we have reflectance values for these, and then we just estimate linear model between the reflectance and digital numbers. So this then also reduces need for all these atmospheric parameters and knowledge. We can replace many steps by this. Of course, there is still unknown that what is the most accurate approach to make this correction. That also it's question about what is possible. I will soon tell some examples about that. Then one topic what we have been working at FGI is this radiometric block adjustment approach. We know what is structure from motion and geometric block adjustment, and we have also this idea of radiometric block adjustment. And the basis here is that when we see the same point from different images, it gives different digital or TN value, and the question is that why does it happen? So this works with multi-view spectral frame imaging particularly. So the idea is that we can model different factors that impact digital number, and then when we have mathematical models, we can estimate the parameters by using multiple overlapping images, and we solve these parameters, for instance, by nonlinear least squares techniques. And then we know the factors that impact DNs, and then we can use it inversely, and then we get corrected images. Like in our previous papers and works, we have shown that this works nicely and eliminates all the non-uniformities. What are there? Then one way to work with radiometric correction is to use this direct reflectance measurement approach. So it's based on the fact that we can calculate reflectance by dividing at sensor radiance, which is the image digital number values that are calibrated, divided by irradiance data. And by this way, we can get reflectance data. So here is the process then. So first we have calibrated sensor, and we calculate at sensor radiances from the image data. We need some laboratory calibration to be able to do that. Then we have this at sensor irradiance data, which is used in this formula. And this gives us actually the hemispherical directional reflectance factors. And then we use some information about diffuse object reflectance, and then we will have these PD directional reflectance factors that can be used to correspond this PRDF. So this is very handy method because it works well even though there are clouds which are disturbing sunlight. Also, it's very good because you don't have to put any panels on object. So when you are working with beyond visual line of sight, if you want to cover tens of kilometers, square kilometers in your flights, and in cases it's difficult to install panels, then this is very handy method. And we have developed at our FGI, we have developed a tool for making this irradiance measurement. It is also not so easy because the drone is tilting, so then the irradiance values are not uniform. So when we have this kind of special tool, then we can compensate for this. Also, here are some paper references where you can see more about this principle. There is also, I'm referring also to this paper, Asen et al. From 2018. There are all different radiometric processing methods are explained there, so I recommend you to read that. Then I have some case study examples. First case study is a tree species classification and inventory in boreal forest. So objective here is to use drone-based technologies for individual tree-based classification and inventory. And this is actually already from 2014, this data, and it is in an area of 10 kilometers. There are 12 separate test plots, and in each of the test plots there are 2 to 6 study plots. So there are more than 4,000 reference trees in this area, and the flight height in this experiment was about 90 meters, and then from treetops it was about 65 in average. So hyperspectral data ground sample distance was 9 centimeter on ground and about 6 to 7 centimeter in treetops, and then RGB data has a resolution of about 2 centimeters. This is also can be found details of this study from this Nevalainen and others from 2017. Here is this we have been actually using this with this feature-based approach, where we have manual feature extraction, and in this case the processing flow is like this. So we have as inputs we have hyperspectral ortho image and RGB ortho image, and then we have point cloud. So this is like data fusion based approach. And then we have feature extraction manually. So we have different structural features and then spectral features. And then from point cloud we also do the tree detection. And then we input here also reference data and make the machine learning. So the hyperspectral data is used in this process only for species detection. And then all other parameters like tree location, tree height, crown diameter, and volume, and this diameter at best height, they are all estimated using point cloud data. And here you can see that there are 347 different features, many different spectral features, and then point cloud features like mean spectra, median spectra, and different continuum removed spectra, and so on. And then also for point clouds, different average, minimum heights, and then different percentiles, and so on. Then a little bit newer approach in this study was this three-dimensional convolutional neural network. Here we did not use all of the areas. It was a couple of areas were not used in this study, and we're using different data layers. We had the RGB bands, we have had the canopy height model, and then we had these 33 spectral bands from the hyperspectral image. And this was also published this winter, Somai, Netsami, and others. And here we had about 3,100 trees for training and 800 for testing set. So here are some results. So about this detection process, it works very nicely in our forests where we have separable trees. So it's quite nice method. This local maximum based method. So when we are using, for instance, search radius of 1.5 meters, we have reference trees and we check that which trees have been found. So there are the detection percents are from 7 or mostly from 70 to 95%. So it works in many situations well. Then about species classification results with different methods. Here we had 4 species, and we used live and out validation with these classical feature-based methods with manual features. The best results were got from random forest and multi-layer perceptron. So this is the random forest and MLP. So they were about 95% overall accuracy. Then our results with this 3D CNN, it was 98% overall accuracy. Some differences were that we had only 3 species in this case, and we had independent test data. So this was the latest result about that. Here, maybe in this slide, interesting thing is to compare that how different features perform. This is this random forest, and we were comparing the use of all features. Then, so there are the like spectral features, and then also 3D features, and also feature selection. And then we had also this only 3D features. So when we used all features, it gives slightly better result than when we used feature selection or only spectral features. The 3D features did not work very well in this study. So it was when we had only point clouds, the overall accuracy was 70%. Then with this 3D CNN, we also tested different feature combinations like only hyperspectral, only RGB, canopy height model, and then hyperspectral and RGB. And with this last case where we had all the data layers, we got the best results. The canopy height model only, it gave poor results. And also with the RGB data only, we also got very good results. It was only slightly worse than this the best result. So here in the perch detection, there were some weaknesses. Yes, so this was about our 3 species and forest inventory experiment. Then one topic what we have been working a lot, and it's very important moment in Finland, is this insect pest infestation detection. So here the objective is to develop efficient tools for mapping and early detection of this bark beetle infestation. This bark beetle, Ips typographus, is a tree-killing insect pest, and it's spreading also to Finnish latitudes because of warming climates. And it has caused really large and extensive forest death in Central Europe and in Canada. And we are trying to find ways how to fight against it. And it's so that first it hits to weakened trees, maybe like storm has made some injuries for the tree, but then when populations are increasing, it's also hitting healthy trees, and it's really bad thing. It's important to develop tools to detect it early and manage it somehow. And how we can then see it. It is seen in the crown symptoms. We are calling green attack the phase where it has first attacked, but we can't see this by eyes, but it's still like hyperspectral sensors. They can detect that there's some changes in trees. Then after a few weeks, when it really hits the tree changes to yellow and brown and finally gray it's dead then. So by spectral remote sensing, we are trying to detect this green attack phase and then to make mapping of different health status of spruces. And we have studied this in one case. We had in southern Finland, city Lahti, we had a campaign both with aircrafts and then with a drone. With drone, we had 4 hectare areas, and with aircraft, we had 3 square kilometer areas. So of course, aircraft covers much larger areas because it flies faster and it's higher, but also then the resolutions are different. So with aircraft data, we had 50 centimeter ground sample distance, and with UAV data, we had 4 to 9 centimeter ground sample distance for hyperspectral data. We had the same sensor in both of the areas. And then what we tried to classify were the ground color. We had the normal green, infested yellow, and dead gray. In this study, we didn't have this early phase green attack detection. And here is also paper that has been published from this study. Here you can see examples about the data from UAV with 10 centimeter ground sample distance and aircraft 50 centimeter. So of course, UAV data is much more detailed. We see individual branches and also the spectral separability of the different classes. Dead is red and healthy is this green one, and then infested is yellow. So it's very well separable here. Like then with aircraft, the separability is not that good. Also, when we see results here, this can be seen here. Also, in this study, we were using support vector machine classifier, and we were using either 22 band spectra or then different normalized channel ratios. And then we were using leave one out cross validation. We did individual tree detection and then made an assessment of performance with aircraft and UAV data. And with UAV, in this case, we had overall accuracy of 81%. And this infested tree had the poorest accuracy of 67%. And then healthy and dead trees had over 80%. Aircraft data had a little bit lower accuracy, especially for the infested and dead trees, but our accuracy was 73%. So we see that it's like, of course, we need good resolution data, so then we can have more reliable classifiers. Then I have my last case study is related to agriculture. So about using drones to monitor silage grass swards. In this presentation, I will talk about dry matter yield estimation and digestibility estimation. So classically, these processes are done quite manually. So somebody is measuring grass height, or farmer should measure it by raising plate meters or different measurement rods. And then concerning the quality, in Finland, our largest dairy company, for instance, they have this kind of a service that farmer can give some grass samples to a milk truck, and then they bring it to the laboratory, and then they get the analysis results. But with drones, we would like to make this fully autonomously and fast. So yeah, in this study, our objective was to develop low-cost drone-based techniques for estimating quantity and quality of grass, and also identify efficient sensors and machine learning techniques how to do it. And it's very rapid and fast process what is required, because while the grass is growing, it's quality also declines rapidly, so there is not so many days to make the decision that what is the optimal day of harvesting. And then crop parameters, what were of interest, they were dry and fresh biomass, and then different quality parameters like crude protein, digestibility, nitrogen content, and so on. And in this study, we were just analyzing this digestibility and then dry biomass. And here is the test site. So it's a second-year silage production field. And there was lots of variation to the crops that was made by using different nitrogen fertilization rates. There were 6 different of those. And there were also 4 sampling dates, and in each date there were 24 samples, so there were 96 samples in total. And as I mentioned, there were many parameters what were in each time were measured, and we were using this dry matter yield and digestibility d-value. And this test setup was made by our collaborator, Natural Resources Institute Finland, LUKE. So here you can see that how this quality and quantity is evolving. So there are 2 to 3 or even 4 harvests per season in Finland. So here we see that by the date, this dry matter yield is increasing, but then this digestibility, this feed quality for the cow, it's decreasing. And here is this green line shows what is the target value for this. So it's very important that you find the correct day to make the harvest to get good enough quality. So the data, we had 4 times hyperspectral data to make the analysis, and then we had this ultra-high resolution canopy height model. And still in this study, we have been using this manual feature extraction with different features, both from spectral and then from this 3D system. So in total, we had 47 spectral features, bands, and different indices, and then we had 5 RGB features, some bands and indices, and then we had 8 3D features. And then in the study, we used these in different groups. We were using only features that we can get from RGB data. There were 13 with 8 3D features, and then these 5 spectral features. And then for hyperspectral, we had 63 features 55 hyperspectral features plus then these 13 RGB features. That was the full set for the all features. And then the estimation process was very similar what we used also in these earlier processes, so that we put these features to run. We were using random forest and multilinear regression, and made some feature selection and model building with Pekka. And then we had output our biomass and d-value maps, and also accuracy estimates of the estimation. And here are some results. So this is from this primary growth trial, and we were comparing different data sets. So we had 3D data, and we had only RGB data and 3D, and then we had the multispectral plus 3D data, hyperspectral plus 3D, and only hyperspectral. And in same figure, we have the dry matter yield and d-value, so these bars, so root mean squared error of the estimation for this dry matter yield. So we can see that the best result we can get with the hyperspectral data. It's not much better than with multispectral data, but still a bit better. And then for RGB, the results were still a little bit worse. And then at the best, we had about 15% normalized root mean squared error. And then for this digestibility value, the precision was about 2%. And again, here we got the best results with the hyperspectral imager, but it was not much better than with multispectral. This was results from random forest. And here you can see still pictures about when we estimate then these dry matter yields for different dates. So you can see results here. So in the beginning, dry matter yield is very low, and in the end, it's high. And we can also see from these scatter plots that reference and estimated values, they are matching, correlating very well. The correlation was 0.97, so it's very good correlation. And our remote sensing data was very powerful to explain variation in this reference data. And here still we were also estimating results in different dates. So we could see that we have this is the primary growth, what we have been mostly analyzing these four dates. So we see that in the first date and in the last date, results are not as good as here in the middle of the growing season. And that's because in the beginning, the growth was not very good. And in the end, the grass was already lodging and there were quality problems also in that. So here in the middle, we had very good quality reference data. So this gave us the best results. And also here we can see that always when we have a hyperspectral data, so hyperspectral data was in all cases, it was giving nicest accuracies. But of course, there are not so big differences between different data sets. Then we had also this digestibility value. I have here only one plot about this. So that was also very successful. So we see again here that in the beginning of growing season, beginning of June, there were overall everywhere was very high digestibility values, and during the growing they were decreasing, and here they were already quite poor in the end of the growing season before the full harvest. So we see that also this digestibility values, they are correlating very nicely with our remote sensing data. So correlation was 0.93. So very good correlation, and this tells us that this spectral remote sensing is a very powerful tool, very good tool for estimating grass parameters. Then we go to the end of my presentation, summary and outlook. So we have seen that hyperspectral features and three-dimensional data, they are giving very interesting possibilities for remote sensing applications. And there are also many other use cases than what I have shown you, but this is very powerful, and in the future we will see much better management of agriculture with the aid of these new technologies. In order to optimize precision in these vegetation-related applications, in many cases it's good to use ultra-high resolution. And then we have seen that hyperspectral generally outperforms multispectral. So multispectral has also done very well, but then when we are going more and more difficult analysis tasks, then hyperspectral is getting better. Like for instance, this green attack phase detection from in this bark beetle study, we expect that this hyperspectral is stronger there. Also, this quantitative processing, one has to know the sensor and calibrate and take care about processing, and then the analytics can be good. And in this analytics processes, we have many times seen that the reference training data, it's very important to have high quality, and some developments in there is important to make. About future developments in our study, we are implementing new hyperspectral sensors in our processing chains, like I already showed. We have some new interesting sensors. And then also we are making quite simple analysis of simple parameters, but then in the future it's necessary to really integrate these individual estimated parameters with the bigger growth and systemic models and holistic farm management. So this is also one, and also holistic forestry management. This is important topic for the future. For us, especially at FGI, we are developing these real-time applications and trying to integrate analytics capabilities to drone. This is called edge computing, and also utilizing cloud processing capabilities to make processing faster, like in agriculture. It's very important to have fast estimates. So this was my presentation. I thank you for the attention and giving me the possibility to give the presentation. I will be happy to answer questions, and then I also would like to thank our funders, this European Meteorology Program, and also Academy of Finland. Thank you.
Thank you, Eija. It is now time. We have several questions from the audience. I will ask Cheryl to send you those questions. But I would like just to deliver your first question. Is related to these seminars are more or less oriented to young professionals. So what do you think about the future of this, for instance, startup companies specialized in high resolution remote sensing for agriculture? Are you aware of some initiatives in this kind of companies in Europe, for instance, using this technology that you have, for instance, developed in FGI?
I think there are a lot of startup companies coming, and we have, like in Finland, there are also, I don't know so many about Europe. I guess that there are huge numbers of companies also there, but just we were in one last week, there was one event where one company was presenting that they are trying to develop these tools, remote sensing based tools for detecting these bark beetle infestations. So they were from Aalto University, which is here in Helsinki, this technical university. So yeah. So there are a lot of interest. So
okay, yeah, good to know that there are already young professionals doing this kind of technical, having this kind of technical competence. We have some questions from the audience. I have some also other questions, but I will leave now Shmalski and Cheryl to introduce the questions from the audience.
Eija, congratulations, it's a great presentation. Abner, I have a question. On which platform do these sensors are placed? Are all on drone based?
So we are mostly using them from drone platforms, but this bark beetle study, we had also aircraft, and we have been installing also this on aircraft platforms, like manned aircraft, I mean, yeah.
Thanks.
And then I think they can be also put on, like carry on hand, they can be used handheld.
It's okay.
Laboratory scanners and so on, yes.
Sherry, you have a question?
I'll read the next question, but first I would like to thank you for the very great lecture. I think it was really amazing to see all these applications of UAVs and remote sensing. It would be very interesting for our members in the student consortium. So we have one question from Rory Neto. So what about sphere sensors or RPAs? Are there some new perspectives?
Yes, so yes, these sphere sensors, they are really coming available, and there are already many new alternatives. Like for instance, this SPECIM sensor, what we have just purchased, so it's 2.4 kilogram sensor. So yeah. And then also I have been amazed when I have been checking the literature recently, so that there are really many new lightweight systems in sphere range also coming available. Yep.
I have another question. Is there any sensor available to measure water depth?
So if there are these bathymetric lidars, so that can be used from drones, and also there are these green lidar that works to some depth. It's of course, if there is a turbidity on the water and you can't see through it, then you can't see. But there are some alternatives also for water depth measurement. And of course, if you have very clear water, then you can also measure bottom using drones. So
Only LiDAR?
like RGB imaging works also there.
The LiDAR uses the green band?
Pardon?
The LiDAR system, you said, uses the green band?
Yes, there is this green LiDAR what can be used. So it works better than photogrammetric imaging. It works with deeper waters also, but not so terribly deep. But in Finland we have quite turbid waters, for instance, so we can maybe like 10 meters or something like this is the limit that we can't go deeper with remote sensing. But if the water is bright, then it works.
I think I would like to add that previously we also had a lecturer, Dr. Annette Eltner. I'm not sure if I'm pronouncing her name correctly, but she actually discussed this topic in the summer school as well. So I think for the person who asked that question, maybe you would like to check that lecture as well to give you more information.
That's okay.
So, yeah, I think I would read the next question. Sorry. So you showed very good results using only RGB images for classifying trees. In what applications do you believe that hyperspectral sensors are essential?
Yes, so it's amazing how well this worked in our case, but however, there were only three tree species. So there were spruces and pines and birches. So it worked very nicely. But then if there are more species, then I think hyperspectral will give some added value. Like in many European forests, there can be maybe typically up to 10 species, and then of course tropical forest is another story.
I am happy to participate today. My team working with hyperspectral data for 3 species classified in a subtropical forest in southern Brazil. It's very difficult.
Yeah. Yes, we have also had collaboration with Antonio about that.
Very interesting.
Yes.
Another question, 992 NV. The question is, how do you analyze multi-temporal drone images? Which calibration procedures are recommended?
Yes, so it's even though you are calibrating the data very well in a single flight, then when you have this multi-temporal data, there is differences between the data sets, so it's not so perfect. So I think what we have been using is so that first you calibrate the single flight as well as you can, and then you can do some mutual calibration of the separate data sets. So for instance, this continuum removal or normalization, it seems to work quite nicely.
Thanks.
Because it's not only the calibration, but also the sun angle can cause differences in shadows and so on. So it's challenging to really evaluate multi-temporal data.
Okay, there are also some questions here on the role of atmospheric correction in this drone-based remote sensing area. Can we neglect this atmospheric correction, or are they important in this drone-based remote sensing processing?
When we have been doing these direct measurements, so that we don't have any reflectance panels on ground, we have seen that atmosphere starts to impact already quite low altitudes, maybe 50 meters or so. So that when we have, for instance, dark objects, then the reflectance get quite bad for the dark objects if we do not make any atmospheric compensation. So,
okay, thank you.
But maybe some like 100 meters or so errors typically that big, but of course for dark targets there can be some challenges. So good to think.
Yeah, so
how to cope that.
Yeah.
I have a question, Eija. Considering that the spectral cameras for URV are still very expensive, with the increase the availability of the spectral sensors on orbital level, what should be the benefits from combining RGB from UAV and the hyperspectral data from satellites?
I think it sounds very good idea. So it would be some kind of super resolution. Yes, I like idea. I don't know if somebody has done it, but I think it's good idea to work with.
Good catch. Okay. Luis Costio Montefinale. The question is, which sensors you use for monitor of the silage grass swards?
So in our cases, we had many sensors. So we had RGB, normal color camera, then we had a multispectral camera, and then we had a hyperspectral camera, and we were comparing these. So this hyperspectral gave a little bit better results than multispectral or RGB in our study, but this is topic that needs to be investigated also further.
Okay. In your study, RGB sensor is the best in accuracy?
Hyperspectral gave the best results. Yeah.
Okay. Daniel Gomes, Dr. Eija, thank you for a great presentation. Could you tell us a little bit more about how you deal with shadows, especially in forests? Do you select the brightness pixels to perform the analysis?
Yes, we have actually many different features. Like when we have an individual tree, then we can either segment it or we can take one circular area, maybe 1 meter diameter, and then there are tens of or hundreds of pixels in this area. So then we can calculate different values. So we can calculate, for instance, brightest pixels and darkest pixels and averages and so on. So there are many features and they are all put to this feature-based classification process. And then we can also make some feature selection.
Okay. Cheryl, ladies first. The last question for you, or no?
From Antonio. Thanks, Eija, for a very interesting presentation. What are the main challenges and opportunities for using HSI systems for accurate nitrogen monitoring in agricultural fields?
Yes, so I didn't give in this presentation these nitrogen results because I thought that it would be too big, too much talk. And I showed this paper, Raquel Oliveira and others, where we have been analyzing also this nitrogen. So we have seen that with our hyperspectral system, we can quite nicely, we get quite good correlations between the nitrogen content and amount and then the hyperspectral features. So for instance, it works with this hyperspectral visible near-infrared sensor, and very interested also to see how it works with a shortwave infrared sensor, because there are some, I have read that it could work even better with this sphere band, but there are good possibilities and it needs some further studies, because nitrogen is of course very important greenhouse gas, and I think this is one of the topics that needs to be monitored, and also for fertilization purposes.
So another question is from PhD student Asgad Kashanu. Thanks for your very clear and inspiring presentation. How is drone tilting considered in the radiometric, not geometric processing chain?
So there are actually two aspects. So as I showed about this direct irradiance measurement, so there we really need to compensate we have different tilt sensors in our systems so that we compensate it. So this is so that we could have this vertical irradiance. And when we are processing like image mosaics, so the calculation principle is such that it kind of eliminates these tilting effects directly. So
okay.
Yeah.
Okay.
Thank you. I think that it's okay. Time to finish the questions because Eija is probably very tired. I would like to invite the attendants to send any further questions directly to Eija. You can find her email in the FGI website. So please, I would like to thanks again, Eija, for a very nice and very complete presentation with many details on very interesting and new topics. For us in Brazil, it's quite interesting, those topics on agriculture and very interesting, very high level presentation. So it's a very good, it's a very good reference for us to follow. Okay. Maybe we can say if you have any further words, it's open.
Yes, so from my point, it was very nice to give you a presentation. I'm very grateful that you invited me, and it was very interesting to discuss with you. So thank you for your invitation, and I wish you very nice Christmas time for all.
It's okay.
Okay, so thank you, Marcus. Thank you, Cheryl, for your nice support and for this very, very good organization. And you are doing a very good job at ISPRS Student Consortium. Congratulations.
So maybe I could say a few words. So I would like to just sincerely thank everyone, like from the speakers like Dr. Eija, and from all the organizers from Brazil. I think it has been really amazing to see your hard work and all of the efforts that you've put into this summer school, because we did not really expect that there will be a summer school this year given our situation. But we are sincerely grateful because I think many of our members are actually looking forward to this great lectures, just like the one that we had today. It was really incredible to see all these applications, all this technology that we are using in our profession. So thank you very much on behalf of ISPRS and the Student Consortium. And I also wish you all a good holiday season, and I hope you can celebrate despite our situation.
Okay, thank you. So thank you, Eija. Nice Christmas for you and your family. Hope you can.
Thank you.
Hope we will see you in Nice next year. I'm not sure how it goes, but
I hope so. We can meet there.
we expect to see all you in Nice to celebrate the end of this terrible pandemic. Okay.
Celebrate with your French wine.
I have a French wine. Okay. Thank you. Thank you for all the attendants. Thank you, Eija. Thank you, Marcus and Cheryl. So this ends the section. Okay.
Thank you.
Thank you. Bye bye.
Bye bye. Goodbye.